Hi, welcome back. So we were talking about bias variance trade-off, and from there we went on to this equation which involved the regularization term. So what we said is that so far we were discussing about minimizing the training error, which was computed as the average error over the M training examples, and this was empirically computed as, say, the difference between the true value and the predicted value, right? And then we realized that if you minimize this, you are not actually minimizing the true error, because this is not a good approximation for the true error. It does not account for this additional term which comes from model complexity. And hence, instead of just minimizing this, it's possible that you might minimize this to 0, but still your true error would be high because your model complexity is high, right? And hence, instead of minimizing just the training error, you should minimize training error plus some regularization term, and this regularization term should serve as a proxy for the model complexity, which means that if the model complexity is high, then this value should be high. If the model complexity is low, then this value should be low, right? So then you are aiming to not just minimize the training error, the empirical training error, but also minimize the model complexity and find some sweet spot in this trade-off, right? That's where we were. And then I said that this kind of forms the basis for many regularization methods. And today we are going to look at a few regularization methods, starting with L2 regularization. Then we look at dataset augmentation, parameter sharing, adding noise to the inputs, adding noise to the outputs, early stopping, ensemble methods, dropout, right? So quite a bit of long list, and we will maybe look at this formula in detail, at least in the context of L2 regularization, right? So let's start there. So in L2 regularization, this is what we do, right? So we define our the loss that we want to minimize, or the effective loss that we want to minimize. We define it as a sum of the training loss, which is this. So which is, again, I'll just write it down once more. This is again summation I equal to 1 to m, or rather average. Oops. M of whatever your training loss is, and we have been dealing with the squared error loss, right? So in the case of L2 regularization, instead of just minimizing this, you also try to minimize this, right? That means you're trying to minimize the L2 norm of your weights, right? That's what this quantity is, and this is some multiplying factor which decide how much weightage should be given to this term in the total loss function, right? So this is the total loss function, and this decides how much weight to be given to this component. If you set alpha to 0, then essentially you are not doing any kind of regularization. Your total loss is just the empirical training loss, and you are back to the non-regularized loss function, right? But if you set alpha to a certain value, it tells you how much do you care about this regularization term. Now the question is, how does this act as a regularization? So this is indeed a function of W, right? There's no denying that. So we wanted the loss function to be of this form, so it is indeed in this form, right? But minimizing this, how does this control for model complexity? That's the question that we would like to understand, right? So what are we saying, right? We are saying that you find me weights such that the training loss is minimized, and also the weights values are very small, right? So what does that actually mean? Suppose we consider only two weights, right? Say W1 and W2. Now in the absence of this, I'm just saying that you go ahead and pick up whatever weight values you want, right? And just minimize my training error. That means I could pick up very large values of the weights, right? So all of the entire R2 plane is open to me, right? So just extend this. So any value in the R2 plane is open to me, right? Now I am saying that, hey, no, you can minimize the loss, but I don't want these W values to blow up, because if these W values blow up, my regularization term will blow up, and hence my effective loss would still be high, right? So I am telling you that here you cannot allow the weights to grow. in other words, I am just drawing some kind of a boundary here and saying that the more you go out of this boundary, right, the more bigger my W1 and W2 are going to be, the more bigger my L2 norm is going to be of the weights, and more bigger this loss term is going to be, and hence my effective loss will not be minimized, right. So now I'm saying that you add as many parameters as you want, you add more model complexity, you have a million parameters, a billion parameters, but for any given parameter I will not allow you to grow those values a lot, because the moment you grow those values a lot, then this loss term will increase, and that will increase my total loss, right. So in some sense I am restricting the model complexity by allowing you to have many weights, but I am not giving you a lot of freedom in choosing the values of those weights, right. So that's how this is acting as a proxy for controlling the model complexity. Okay. So now if that is the loss function, then we are interested in the derivative of the loss function with respect to W, right, because for all gradient descent methods and its variants, this is what our quantity of interest is. So the derivative of the quantity on the left hand side is the derivative of this quantity plus the derivative of this quantity with respect to W, and this quantity is actually alpha by 2 W transpose W. So if you take the derivative of that with respect to W, you can think of this as W square. So one of the W's will disappear, and you'll have a 2 term here which will cancel with this. So W square is, the derivative is 2W. So the 2's will cancel and you'll just be left with alpha W, right. So that's how you can think of how we arrived at this formula, right. Now, so now what happens to your update rule, right. So your update rule earlier was the new value of loss is equal to the old value minus eta times the derivative, and now this is what your derivative looks like, right, and I've just opened up the brackets. So this is what your earlier update rule would have looked like if you did not have the alpha term. Now since you have the alpha term, this term gets added, right. So L2 regularization is very easy to implement. If you have already implemented gradient descent, then all you need to do is change this update rule and add this term or subtract this term, and you have the L2 regularized update rule for gradient descent, right. Now this becomes more complicated as you look at other algorithms like Adam and variants of it and so on, but we will not discuss those. But at least in the case of vanilla gradient descent, where the update rule was just move in the direction opposite to the gradient, it's now subtract that term and then further subtract this term. That's all your update rule is. So extremely easy to implement. Now let us see what is the geometric interpretation of this, right. So to understand the geometric interpretation, we will do slightly longish, I would say, a derivation, right. We will just try to go a bit deeper into what the Taylor series says, and from there what do we derive and so on, right. So let's assume that W star, okay, is the optimum So let's assume that W star is the optimum solution for LW. So LW, remember, was our unregularized loss function, right. So our new loss function is L tilde W is equal to LW plus this alpha by 2 into W transpose W. So this LW was our unregularized loss function. So let's assume that the optimal solution for that was given by some W star. Right, there's some W star which exists, which gave me the lowest value for LW, right. So that's all we are defining, right, and there's no problem with that definition. Yeah. Now consider a point which is say a point W, which is in the neighborhood of W star, right. So the way to write that would be W is equal to W star plus U. So there is a point W which is in the neighborhood of W star. The other way of saying that is that let's consider a jump such that you have W minus W star, right. So you could think of it this way. This is more natural, that we are looking at a point W which is in the neighborhood of W star, and from that equation you can derive this equation, right. So that's the small jump that you have made. Okay. Now we'll now do a bit of reasoning or a bit of derivation starting from there, right. And now let's see what the Taylor series says, right. This is Taylor series second order approximation. So far in this course we have been dealing only with the first order approximation, but now I'm talking about second order approximation. And what this says is that the loss function in this neighborhood, right? So W is the point in the neighborhood, is the loss function at W star plus the first order term plus the second order term, right? So you already know this from the Taylor series that we have seen earlier. And now the interesting thing here is that this term is 0. Why is that 0? Because that's the optimal for the loss LW, right? And if it's the optimal for the loss LW, then the derivative at that point is going to be 0, right? It's going to be some minima, and at the minima the derivative is going to be 0, right? So that's why this quantity is going to be 0. And now I'm just going to expand this, right? So now what I have done here is this quantity has disappeared, and this u I have written as w minus w star. So wherever I see u, I have substituted as w minus w star. Nothing great again about that. And this delta w, this quantity has disappeared. So I'm just left with the first term and this last term here. Okay, that's what my LW looks like, where LW is the unregularized loss. Now let's just look at a few other quantities. Yeah. So now this is the if I compute the derivative of this, right? So this is what my LW was. Now if I compute the derivative of this, that's the same as the derivative on the of the quantity on the left hand side. So I can take the derivative of this quantity, and I can just open up the brackets. I have derivative of LW star plus H into W minus W star, right? So this again you can think of this as x h x, right? So you are kind of taking the derivative of a quantity which has x square, right? And the derivative of that, one of the x's would disappear and just left with x, and in this case x is W minus W star, and there will be a 2 coming out which will get cancelled with this, right? So that's how you can think of this derivation that I have written here. So this is what I get, right? So the derivative of the loss function with respect to W turns out to be H into W minus W star, and we had seen earlier that this H is actually the Hessian, which is a matrix containing the second order partial derivatives, right? So we had already seen this in a earlier lecture, so I'll not repeat that. Okay. So there's nothing great here, right? I've just applied Taylor series, then done some simplifications. I mean, just taken some derivatives. So I have just a set of steps which you can, which one step follows from the previous, and you could just go back and look at this if you have any doubts. But there's nothing conceptually difficult that I've done here. Okay. Now from here, let's now look at this loss, right? This is our regularized loss, and the derivative of the regularized loss, as we had derived on the previous slide, was this plus alpha w, right? This we had derived. So remember, LW is equal to LW plus alpha by 2 W transpose W. So now if you take the derivative of this with respect to W, so here this derivative, all of these are derivatives with respect to W. It's obvious from the context, so I have not suffixed it explicitly, but it's derivative with respect to W. And so this would just be derivative of this quantity plus the derivative of this quantity, and the derivative of this quantity, as we saw on the previous slide, was just alpha W, right? So again, nothing new that I have written here, but now what I'm going to do is I'm going to try to use this value instead of this quantity here, right? That's the main change I'm going to do as I go ahead. Okay. Now let there be another W, which is the optimal solution for the regularized loss, right? So now if there's such a W tilde exists, then the derivative of the loss function at that point would be 0, right? And now we have seen that the derivative of the loss function at any point was given by this formula. We just saw this on the previous slide. So I've just substituted that formula instead of this formula, and instead of the generic W, I have substituted W tilde, right? That's the only change that I've done here, right? Yeah. Again, I'm just doing a lot of steps, but there's nothing much going on here, right? Just like I'm defining some quantities and then using those quantities, and at some points I'm using the properties that the derivative is 0, right? So again, there's nothing to really say much about here, right? At this point, once we reach the final answer that we are looking for, then I'll have significant things to say. Now this I can rewrite it as I've just opened up the brackets here. So this is H W tilde minus H W star plus, sorry, W plus alpha W tilde equal to 0. So, I have taken all the W tilde terms on one side, right. So, it is H W tilde minus the plus, sorry, plus alpha W tilde is equal to H W star, right. And this alpha, I can write it as alpha I. It does not make a difference. It's just multiplying by the identity vector. So, I into any vector is the same as that vector, right. So, it does not make a difference. So, that's all I am doing here, and then just regrouping the terms. So, this is how I arrived here. Now I get a formula for W tilde. And why do I know that this inverse exists? Because I have gone ahead and straight away taken the inverse. How do I know that this inverse exists? Because H is the Hessian matrix. So, H is a positive semi-definite matrix, and hence the inverse exists, right. So, that is why I can write it as this quantity here, okay. So, continuing in my journey. Now, as alpha tends to 0, right, if I do not use a regularization, right, if this quantity is 0, then this term disappears, and I just get H inverse H W star. So, in that case, my W tilde is actually equal to W star, and that should indeed be the case, right, because if alpha is 0, that means my second term was not there. If the second term was not there, then I am just left with my original loss function, and for the original loss function, I had already defined that the optimal is W star. So, if I am going to get rid of alpha, if alpha is equal to 0, then even for the regularized loss, which is just equal to the original loss, my W tilde equal to W star, right. So, simple observation, but just trying to make the point clear. Okay. Now, we are of course not interested in the case of alpha not equal to 0, we are interested in the case when alpha is not equal to 0, right, because we are using regularization, and in that case, we want to see what is this relation between W tilde and W star, okay. So, let us go ahead. So, since H is a symmetric positive semi-definite matrix, we know that its eigenvalue decomposition will exist. Not just that, we know that its eigenvalue decomposition, the eigenvectors are going to be orthogonal. So, I can write it as Q lambda Q transpose. So, I am sure you have done this in a course on linear algebra. If not, there are these other videos that I have on linear algebra. You can go ahead and look at that. I do eigenvalue decomposition in quite a bit of detail there, right. So, this I would assume you know that any matrix you can write the eigenvalue decomposition, and Q is orthogonal here. So, Q transpose equal to Q transpose Q is equal to I, right. We know that. So, now on the previous slide, whatever I had, I am just going to bring that back. Okay, this pen work is fairly cumbersome. I need to get rid of. Okay. And now instead of H, so this is what we had on the previous slide, right. So, this is what we had derived so far, and I am just bringing that back, and wherever I see H, I am going to substitute the eigenvalue decomposition of H. Again, all of this is nothing great happening here, right. It is all just a series of steps that I am doing. I am trying to reach a point after which I can make some conceptual comments, right. I can get some insights into what is happening into L2 regularization, right. So, right now I am just going through the drill. Now, I am just going to do a few more simple things. Yeah. So, again, instead of I here, I have written it as Q I Q transpose. So, Q into I is of course equal to Q, and then Q Q transpose is again equal to I. So, there is no harm in writing this. This is correct, right. And now, once I have done that, I can now regroup some terms, and I can write it as the product of 3 matrices here, right. So, I have taken the middle part as common, which was alpha, the triangular matrix lambda, which is the matrix of eigenvalues of H, then alpha I, and then I have Q here and Q transpose here, right. So, I have just regrouped the terms. Now, this becomes like the product of 3 matrices A, B, C, and I am trying to find the inverse of this product. Then the inverse is going to be C inverse into B inverse into A inverse, right. So, that is what it is going to be. So, I can just do, that is where I am headed now, right. So, I will just do that. Yeah. So, I can write it as Q transpose inverse, then lambda plus alpha I inverse and Q inverse, and this Q inverse and Q will multiply out and give me I, and Q transpose inverse is of course Q, because Q is an orthogonal matrix, right? So a few things have got simplified for me now. Yeah, so this is where I end up with, right? And here again I would notice that if alpha is 0, right, then this term disappears. I am left with lambda I inverse into lambda, so that will also disappear, that will become I. Then I am Q transpose into W transpose. Q transpose will again become I, so I'll just be left with W star, which means in the absence of regularization, my W, or when I set alpha to 0, my W tilde is equal to W star, which is the same as saying that if I don't use a regularizer, my optimal solution is W star, right? So I'm just saying this again to make sure that in the steps that we have done, we have not made any mistake. Things are still looking meaningful in whatever we have done. Okay. Yeah, so let's just go ahead a bit now. Yeah, so now I can write it as W tilde is Q D Q transpose, where D is this matrix. So this is a diagonal matrix. This is also a diagonal matrix. So the sum of two diagonal matrix is going to be a diagonal matrix, and then you're again multiplying it by a diagonal matrix. So that's also going to be a diagonal matrix. Hence I am calling it D as the diagonal matrix. So now W tilde is equal to this quantity, right? So now I have reached somewhere that I wanted to reach, and from here on I can start hopefully start making some observations, right? So let's just work with this. Yeah. So this is where we are. We had a derivation for W tilde, and we have now been able to express W tilde as a function of W star with these matrices Q, D and Q transpose, right? So what exactly is happening here, right? So W star was my optimal solution for the unregularized case. Now when I am using the regularization, what is happening? W star is first getting rotated by this matrix Q transpose. Okay, so this will give me some, let's call that quantity as Z, right? So Q transpose W star is again going to be a vector. So Q here would be an n cross n matrix. W is an n cross 1 vector. So the result is again going to be n cross 1, right? And now that is getting multiplied by again an n cross n diagonal matrix, right? So now multiplying by a diagonal matrix, if you only have the diagonal terms and everything else is 0, and if you multiply the vector by such a matrix, then it's the same as taking every entry of the vector and scaling it by the corresponding diagonal element. So there are n diagonal elements and n entries in the vector. So this multiplication, the result that you get is simply every entry of the product is actually this corresponding entry multiplied or scaled by the corresponding diagonal element, right? So that's what is going to happen here, and so on, right? So that's what the diagonal multiplication looks like. So first you rotated it, then you scaled it by D, and then again whatever you got. So let's call that Z1, right? So this was my Z. Now I got a Z1, and again I am taking Z and rotating it by Q again, right? So that's what I am doing here. So this, I've made this observation. Now what does this mean and so on? It's still, that's something that we need to understand. But this is what is happening here from a linear algebra perspective, right? So W star first gets rotated by Q transpose to give Q transpose W star. However, if alpha is equal to 0, right? If alpha was 0, then this just becomes this whole thing here. Just becomes I, right? If alpha is equal to 0. And then Q transpose rotated W star, then Q rotated it back in its original position, and we got Q, right? Because Q and Q transpose are inverses of each other, hence because Q is an orthogonal matrix. So there was no effect if alpha is 0. Again, just saying this for the sake of showing that whatever we are doing is sounding correct, right? But if alpha is not equal to 0, then what is happening is the question, right? Then what does D look like? So first, D has two components. So first component is this. So let us look at what that component looks like, right? By this I mean the whole of it, right? So first lambda plus alpha I. So you have, So you have a matrix which contains the eigenvalues on the diagonal, everything else is 0, and you're adding the alpha I matrix. So it has alpha all the way on the diagonal, and there are n of these alphas. So you're adding these two matrices, so you'll just get lambda 1 plus alpha, lambda 2 plus alpha, and so on the diagonal, right? Now the inverse of a diagonal matrix is just the is just another diagonal matrix containing the reciprocals of the diagonal elements, right? So this would be what the inverse would look like. Every element on the diagonal would be the inverse of it, right? So this is what is happening here. So each of these quantities is just going to be the inverse of that quantity. Now d is actually this further multiplied by lambda, right? So this is what d is. So now let me again try to multiply it by lambda. Yeah. So this is what I'll get, right? So I had this matrix, and now I am multiplying that matrix by another diagonal matrix, and it has lambdas on the diagonal. So if you do this multiplication, you will just get the product of these diagonal elements on the product matrix, right? So that's all you will get. Okay, so this is what this middle guy here looks like. Okay, and if alpha were 0, then the middle guy would just become I, or this would all disappear, so you'll just get I, and there is no change happening. W tilde is equal to W star. But now if alpha is not equal to 0, then what exactly is happening here, right? So each element of I of Q transpose W star, right? So this is the first multiplication that is happening. Now each element of that vector is getting scaled by this quantity, right? And after it gets scaled by that quantity, it is rotated back by Q. That is what is happening, right? The rotations performed by Q transpose and Q are inverses of each other, but in between this scaling is happening, right? And now if the eigenvalues is very large, if it's greater than alpha, right, then this quantity that you have on the diagonal is actually going to be equal to 1, right? So that means for those weights there will be no scaling which will happen. They will remain the same as their original value, right? So remember, this W star is a vector of weights, and we are talking about every element of that vector getting scaled, but we are just seeing that if the eigenvalue is large, then those weights will not get scaled. Let's suppose lambda 1 was very large, then no change will happen to this guy. Similarly, if lambda 2 was very large, then nothing would happen to this guy, because lambda by lambda plus alpha would almost be equal to 1. Right? Now, on the other hand, if lambda is very less than alpha, then this quantity almost becomes 0. That means whatever elements were there, if this is what your W star was, and say this is the ith element, if the corresponding ith eigenvalue was very small, then it is almost like this weight will go to 0. And this is actually what we wanted. What the effect that we were hoping for was that some of the weights should shrink, because if all the weights are large, then your L2 regularization term, which is W transpose W, is going to be high. And now what we are seeing is that if the eigenvalues are small, right, then those weights are going to shrink a lot, and that's exactly what we were hoping for. And the other weights will remain the same as what they were earlier, right? They will not grow, but they would remain the same as what they would have been in the absence of regularization, right? So now you are seeing the effect that certain weights are shrinking here, and that's a proxy for controlling the model complexity, because now you are not allowing the model to do what it wants. You're not giving it, you're given it capacity, but then you have not given it the freedom to fully utilize this capacity. The full capacity would be, I should be able to take the weight W1 and set any value between minus infinity to infinity, but now I am not allowing you to do that. I have given you as many weights you wanted, but on each weight I have now drawn some boundary, and if you go out that boundary, then W transpose W is going to increase, and this regularization term is going to ensure that some of those weights actually decrease, actually shrink, right? Now, still we need to look at a few more things here, right? So effectively what will happen, the significant directions where there are larger eigenvalues, those will be retained because those are not getting scaled. But the directions where the eigenvalues are small, those will shrink and those weights will be heavily penalized. Right? They might almost go to 0. And now if you look at the effective number of parameters that your network has, then this is the effective number of parameters. Right? Because your total number of parameters was n. Now many of those parameters are getting scaled down significantly by this factor. Right? Now depending on how many are getting scaled down, if you take this summation, this would be less than n. So effectively you have ended up reducing the complexity of the model, right? Because you started off with n parameters, but now because of the scaling, not all of your n parameters are fully effective, and hence the effective number of parameters that you have is actually much less than n, right? So that's what is happening. That's how it is controlling the model complexity. Okay. Now let's just look at a bit more of geometric interpretation also of this. So now what I'm showing you here are two loss contours. So and we are using the same. Oops. So this is my LW. So this is what my unregularized loss looks like. This is my alpha W transpose, sorry, not alpha W. This is what my W transpose W looks like. Right? So this is the regularization loss, and you can see that that loss has this. If you look at this this contour here, this is the contour of a bowl, which is the contour of a square function, and indeed it should be the contour of a square function because this is a square function, right? So this is the place where W transpose W is equal to say 1, W transpose W equal to 2, 3, and so on, right? So these are the contours that you have here, and these are the contours of W, right? Now let's make some observation about these plots, right? And what is W tilde? W tilde is the place where these two plots are intersecting, right? Of course, I could have drawn some more, this contours will go on, right? And similarly, I could have expanded this contours also. So there are many places where these two plots will intersect, right? It's not that this is the only place that they will intersect, but this is where my final solution came out for this problem. This is the W tilde that I ended up with. So W tilde was the optimum point for L tilde, where L tilde was L theta plus omega theta, right? And this is L theta, and this is my omega theta. Okay, so that's what is happening here. Now I want you to look at this plot, right? So I'll now we want to look at this plot and try to understand how this relates to the geometry and how this relates to the idea that certain weights are actually shrinking. What exactly is happening here, right? So I want us to pay attention to all of these. So I'll clear these drawings because we understand what each of these plots corresponds to, right? Now in the absence of regularization, this is what your W was, W star. So that means it had taken this value along the W1 axis and it had taken this value along the W2 axis. Okay, so you can see that these W's are relatively large, right? Now in the presence of regularization, this is what my solution looks like. Let me just change the color. So this is my value for W2 and this is my value for W1. So indeed my weights have shrunk, right? Not just that, my weights have not shrunk uniformly, right? It's not that W1 has become half its original value and W2 has also become half its original value. You can see that W1 has decreased much more as compared to W1, right? So first observation, yes, indeed my weights shrunk. The second observation, that the weights have not shrunk uniformly. They have shrunk by certain different factors, and that is expected because those factors depend on the eigenvalues. So those factors are lambda 2 by alpha, right? Now the question is, why did W1 shrink more than W2, right? And to understand that, you need to look at this loss surface here. Now, if you look at that, you should be able to understand why. If W2 has shrunk more, then that means W2 is not so important as compared to W1. So if you look at this loss surface, the solid loss surface, does it give you that impression? That's the question I'm trying to ask. And indeed it does, right? So I'll tell you why. So if you look at this direction, which is the W2 direction, then here you can see that the distance between the contour lines is very smaller as compared to the distance between the contour lines along this direction. So this is the W1 direction and this is the W2 direction. What does that tell us? That along this W1 axis, even if I change the weight a lot, I'm not losing much in terms of my loss, right? So I have more flexibility here. If I want to shrink the weights, then I have a better chance of shrinking this weight, because whatever is the optimum value for this weight, even if I shrink it, my loss is going to shrink a bit more slowly because there's a higher gap between the contour lines here. So the loss is not rapidly changing along this direction. But along the W2 direction, you can see that the loss is rapidly changing. So now if I were to aggressively shrink W2, then even for small shrinks in W2, my loss will increase, right? And that is not acceptable to me, because I want to shrink it, but I also want to maintain this trade-off that this loss should also be small. I want my W's to be small, but I also want this loss to be small. Hence, I have ended up with this trade-off that the weights which are more significant, right, which was W1 in this case, I am shrinking it less, because if I shrink it a bit more, if I had brought it down to this value, then my loss would have been even higher, right? And that is not something that I want, right? Whereas when I am shrinking W1, I have more leeway, because along this axis, my loss is less sensitive to changes in W, because by a small change in W, my loss is also decreasing slowly. That's what is indicated by the slope, right? So this gap, if you remember, indicates the slope. The slope here is smaller. That means a small change in W does not cause a large change in the loss, right? Whereas along this axis, the slope is steeper because this gap is small. So small change in W causes a large change in the loss, right? So this figure kind of summarizes everything that we wanted to understand about L2 loss. It tells us what does the shape of L2 loss look like. It tells us what the optimum is in the absence of L2 loss. And then it tells us how there is a compromise being made where you're shrinking the weights, but you're not shrinking all the weights uniformly. You're shrinking them according to different proportions, and that's exactly what is happening here. And these proportions actually are decided based on which directions are important and which directions are not important, because the eigenvalues, these are, remember, the eigenvalues of the Hessian, and the eigenvalues of the Hessian tell us which directions are more sensitive and which directions are less sensitive, right? So I'm not proving that, but you can go back and look at that. The eigenvalues of the Hessian matrix, these were the eigenvalues of of the Hessian matrix. So these tell us which directions are more important and which directions are less important, right? So all of this has now fallen in place, and this picture kind of summarizes what happens with L2 regularizations. So that's all I had about L2 regularization. I'll end this video here.